Good afternoon, everyone. My name is James Colliander, and on behalf of CRM, Fields, and PIMS, I'm the director of PIMS. I'm pleased to welcome you today to the second lecture in celebration of the 2020 CRM-Fields-PIMS Prize winner. Professor Sulem from the University of Toronto will speak on the derivative nonlinear Schrödinger equation, global existence, and soliton resolution. Once again, congratulations, Catherine. I look forward to your lecture.
Thank you very much, Jim. Today, I will talk about the derivative nonlinear Schrödinger equation, and I will discuss the question that refers to its existence for all time and what's called the soliton resolution that I will explain very, very soon. So first, I would like to acknowledge the collaboration with my colleagues, Robert Jenkins from Central Florida University, Jackie Liu, who is now tenure track in Chinese Academy of Science in Beijing. He was a student of Peter Perry and a postdoc in Toronto. And Peter Perry is from University of Kentucky in Lexington. So the derivative nonlinear Schrödinger equation is an evolution equation, nonlinear, which is written here. The unknown function u is a function of two variables. X lives in R, so it's a one-dimensional, one-space dimensional equation, a function of x and t. And with value in complex, u is a complex function, complex valued function. It looks very much like the canonical Schrödinger equation, at least it has the same part of the linear part. It has the particularity of having a derivative in front of the nonlinear term here. And that's why it has the name derivative nonlinear Schrödinger equation. As you see, I put here a plus or minus. So unlike the usual nonlinear Schrödinger equation, for which the plus or minus refers to a focusing or defocusing equation with different properties, for derivative NLS, these two equations are essentially the same. One can, the solution of one of them with the plus sign can be mapped to the solution of the minus one with the change of x to minus x. So in the following, I will just stick to one sign, the plus sign. So this equation, it comes, it's a model that was derived by plasma physicist Mollius in '76, and other people and other contexts, from the compressible magneto-hydrodynamics equation for conducting fluids. And the first restriction is that the velocity and the magnetic field depend only on one space dimension, function of x only. So the second assumption is that the magnetic field, who has three components, for the first component, it is constant. It is a uniform background magnetic field along the x-axis. And well, the second assumption is that one considers or restricts themselves to a regime that is called the long wave small amplitude and proceeds with formal asymptotics. And if you remember yesterday, we discussed the water wave problem, and this asymptotic led to the Korteweg-de Vries equation. In the case of conducting fluid, the model is not Korteweg-de Vries, it's this equation, the derivative NLS. And U is in fact the complex transverse magnetic field, so it's constructed from the two other components of B, B2 and B3, by constructing this complex function. So that's the original, I mean, the physics origin of this equation. And so when one is interested in the dynamics of nonlinear waves, there are essentially two main phenomena that may occur associated to this, and these phenomena are really fully nonlinear situations. One is wave collapse, and the other one is existence of solitary waves. So wave collapse is a process in which a wave becomes singular in a finite time. And what is really interesting is that the singularity depends on the physical model. So I have listed a few different situations here. In optics, the self-focusing, the singularity corresponds to a self-focusing of very high intensity laser beams. In particular, in the case of ultra-short laser pulses, it has applications to optical communication, medical imaging, and even eye surgery. In water waves, the singularities corresponds to breaking of waves, and this breaking is associated to second derivative of the elevation becoming infinite. Another important problem in propagation in dynamics is collapse in plasma. So in plasmas, singularity corresponds to region of very low plasma density and strong amplification of the electric field. They are a basic mechanism for transferring energy from large to small scales, and they permit dissipative processes to heat the medium. And the last example, but there are many others, is breaking of acoustic waves that is associated to shock waves and in particular the formation of strong gradients. On the other hand, solitary waves, they exist as a balance between nonlinearity and dispersion. And physicists are really interested in their, I mean, we are all interested in their existence, but I would say physicists are more particularly interested in their resilience, their stability, the fact that they survive for very long time. And another important aspect is how they interact. So it is in this context that I will address the questions. Do solutions to the derivative NLS exist for all time, or may singularity occur? We will see that this the NLS has soliton solutions. Are they stable in the sense of are they stable for very long time? And also another important concept is the notion of soliton resolution, which refers to long time behavior again. And to explain soliton resolution, I will simply quote some thoughts by Terry Tao in a paper that he wrote in the bulletin of the AMS. The title is Why Are Solitons Stable? And he says, it is widely believed and supported by extensive numerics that for many dispersive equations, roughly speaking, those whose nonlinearity is not strong enough to cause finite time blow up, and more precisely for subcritical equations, solution with generic initial data should eventually resolve in a finite number of solitons, moving at different speeds, plus a radiative term that goes to zero. This rather vague defined conjecture goes by the name of the soliton resolution conjecture. So this is also one part of our questions, whether this phenomenon of decomposition in separated soliton happens for the derivative analysis. Okay, so this is the outline of the talk. First, I will present the basic properties of this equation, and then also the statements of our results. And to put this statement a little bit in perspective with the recent development, I will also present a number of recent advances in integrable PDEs and how these techniques of PDEs and inverse scattering have been combined successfully. Then I will go back a little bit in time and give some historical notes about the integrable system to see how questions moved, how progress were accomplished. And in particular, I will use the defocusing nonlinear Schrödinger equation as a model to show the milestones in the progress of the understanding of inverse scattering. And then I will see how these techniques, we were able to apply them in the context of derivative nonlinear Schrödinger equation and get the results under the consideration. Okay, so this is the first section, the basic properties of solutions. So I have rewritten the equation here. U is a complex valued function. X lives on the real line. And the first important property that comes in the analysis of these PDEs is to observe scale invariance. If U is a solution of the NLS equation, then the function U lambda constructing from this solution by scaling, appropriate scaling of the independent and dependent variables is also a solution. And we observe that in particular, this the L2 norm of these two solutions, U and U lambda, are the same. It is referred to the equation is L2 critical. So L2 critical in this setting of dispersive problem gives an information that things might be difficult, that different scenario may happen, and it's unlike what Terita was saying about subcritical. Well, L2 critical is a difficult situation in general. This equation has conserved quantities that are listed here. The first is the L2 norm. The second is called the momentum. And the third is called the energy. It, as we see here, it doesn't have a definite sign. Two quantity positive and something that has no sign exactly. So the first question that people ask is the solution well posed during a finite time, saying that assuming that U0 is an appropriate Sobolev space, can the solution be well defined during a finite time? And this question was studied in the 80s by Tsutsumi and Fukuda, and then many others. In the 80s, the people would essentially assume that the solution is relatively smooth in Sobolev spaces where one can define, in particular, the energy, so what we call energy space. Later, there was an effort to reduce the smoothness of the initial condition, and Takaoka reduced, so as I will explain in the next slide. Now, from a solution that exists for a finite time, the next question is, can it be extended for all time? And the answer that was given in the 90s was yes, if the initial condition is small in L2. And in the context of initial condition in the energy space, Hayashi and Ozawa showed that if the L2 norm is small enough, and they found that small enough smaller than square root of 2 pi, then the solution exists for all time in H1. And this result was extended for solution with less regularity, and it was almost optimal that if U0 is in H1, half plus a little bit, then and the L2 norm is smaller than the square root of 2 pi, the solution exists for all time. This work was done by Jim Colliander and I team with Kiel, Stafilani, Takaoka, and Tao. And I said it was almost optimal because it was at the same time proved that if U0 is in a Sobolev space of index smaller than 1/2, then ill-posed happen. Then this result was improved by Wu in H1, and then by Guo and Wu in H1/2 by pushing this constant to square root of 4 pi. And we will see these constants are not any constant, they are related to L2 norms of solitons. In the same spirit as what Michael Weinstein in '83 discovered in the context of NLS, the usual NLS. Now the next question, once people have global well-posedness, is how does the solution behave for a long time? So this result that I quote by Hayashi and collaborators in '99 assumes small initial condition with quite strong properties of smoothness and decay. And they found that as t goes to plus or minus infinity, they proved a very precise behavior. The solution behaves like 1 over square root of t. And they proved that the rate of decay in time, existence and uniqueness of asymptotic states U plus and U minus, and a phase. And it is interesting to notice that the phase contains a logarithmic correction that also happens in 1D NLS. It's not an unusual result. And they prove this result. This is a pointwise estimate. Now, another important property among this basic property is the existence of bright solitons. So these solitons, they depend on 4 parameters. And these parameters, I call them omega, C, x0, and theta 0. And these soliton solutions have the form of an amplitude, phi, and the phase, have an amplitude and phase. The amplitude depends on y, so y is x minus ct, so it's soliton that moving with velocity c. It could be c positive or c negative. X0 is arbitrary. And this amplitude has is an explicit form, square root of 1 over the hyperbolic cosine. So it's a little bit look like the soliton of KDV or NLS. So it's a well understood, it decays very fast at infinity. It is symmetric. And it has a phase. The phase is linear in t, linear in y, and with a correction in the form of this integral. So it's quite very explicit. And the 4 parameters, as we see omega, c, the velocity, and x0 and theta 0 are constant that come from the fact that the NLS is invariant by translation and by multiplication by constant phase. Now, when these 2 parameters, omega and c, satisfies that for omega equals c squared, that's gamma equals 0, this soliton that decays exponentially fast reduces to what's called an algebraic soliton or a lump soliton that decay not so fast, like 1 over y at infinity. And one can calculate explicitly the L2 norm of this soliton for all values of omega and c. But what is important to notice is that it is always smaller than 4 pi, and 4 pi is the L2 norm of that limiting soliton, the algebraic. So it is in fact the same 4 pi that happens here. And once one has soliton, the question is its stability. So orbital stability is not asymptotic stability that I was talking before. It's a weaker information. It refers to the fact that the soliton is stable, but up to a certain number of transformations which leave the equation invariant. And there was work by Killam and Otta in 2006, proving this orbital stability for 1 soliton and extended for n soliton. So n soliton is a little bit more complicated solution. We will see it a little bit later. Somehow n soliton behaves like, when t goes to infinity, n soliton behaves like the sum of n separated soliton that each moves at its own velocity. And there was also a result about this algebraic soliton up to all these transformations that leave the equation invariant, in particular the scaling in transformation. Yes, so what are the questions? From this basic property, one would like to ask the question, can global well-posedness, does global well-posedness hold for large L2 data, or do singularity may occur? How do these soliton solutions behave? In particular, are they asymptotically stable? And in reference to this soliton resolution, and what happens for generic initial condition, how does this soliton resolution, which means the separation in a finite number of soliton as t goes to infinity, occur? And in the course of 5 years or so with my colleagues, we worked on this question, and we were able to answer them, not being limited to the PDE methods, but using a property that is really very important in the dynamics, is that this DNLS equation is solvable through the inverse scattering method. And that was discovered by Kaup and Newell in 1978. Yes. So I will state the results, and you will see, especially for the long time behavior, it will be a little bit vague because otherwise it needs a lot of notations, but I will explain it. So the result we obtained were the following. First, we worked with a variant derivative NLS equation which is equivalent but a different form. It is the equation obtained from this one by introducing a new function q and multiplied by a gauge term. And this function q satisfies the following equation here. And the two equations are equivalent. People have used different gauge transformation for different purposes. This one is quite convenient in the context of the context of inverse scattering. So the first result, in fact, this result, that's the one that gave us the most, that was the hardest, that was the last we obtained only recently. it's the global well-posedness for general initial condition without any additional conditions. So we assume that Q0 is in H22. So it is a quite restrictive assumption. We assume that so here is the H22 norm. The function, so it's quite an assumption on the smoothness and decay. So smoothness, we assume that the function Q0 is in L2 and its first and second derivative are in L2. And we assume also fast decay. So this is certainly a point that we may invite improvement, but at least at this moment that we were only able to do that with these assumptions of smoothness and decay. And the result is that there exists a unique solution of this equation, and thus by consequence to the original derivative NLS with this initial condition, such that it is a continuous function of time for all time with value in this Sobolev weighted space. And the flow map that associates to QZ to the initial condition, the solution is Lipschitz continuous from H2 to H22 to this space for all time. The second result is the long time behavior. And as I said a little bit before, I did not put a lot of information because it would require a lot of notations and pretty heavy, but I will try to explain what this long time behavior says. So again, we assume that this Q0 is in H22, and then we will assume some additional conditions that are referred in as genericity conditions that I will explain a little bit later. It is related to some properties of the scattering data that comes along when applying this method of inverse scattering. So the theorem says that for such initial condition, as t goes to infinity, we consider in the xt plane some space-time cone. Here it is the space-time shaded in gray. And we ask, how does the solution behave for x and t goes to infinity as inside this cone? And the answer is that it approaches a soliton plus a correction to the soliton that decays fast and disperses. So what is this soliton? How do we find this soliton? Well, the initial condition Q0 has associated to it hidden scattering data, I would say. And in this scattering data, there are some hidden solitons, a finite number of solitons. And all these solitons, they move with different velocities. And when we are in this cone, we see only those whose velocity is between precisely, I think, minus V2, between minus V2 and minus V1. So it identifies those, and the others, they move too fast or too slowly, so one does not see them. Now, the theorem gives precise expression for these quantities. In particular, F contains the terms that comes from the interaction of the various solitons between themselves, interaction of the soliton with the dispersive part and also a pure dispersive part. But the formulas are quite complicated, so I did not write them down. Now, corollaries to this long time behavior is that soliton solutions are one soliton solution are asymptotically stable, meaning that if one starts with the initial condition close to one soliton, as time evolves, the solution will remain close to that soliton with the parameter of the soliton will be close to the original one. So there will be some modulation. And in particular, another consequence of this long-time behavior is the soliton resolution, that asymptotically in time, the function decomposes into a sum of individual solitons plus a dispersive part. So after having presented the result, I would like to make a little diversion and to present some recent advances in dispersive PDEs and how the inverse scattering brought new understanding. So I will here the first example that the first problem I mention is about what's called the cubic Szego equation for on a torus, on a one-dimensional torus, which is written in this form. So X is in the torus on this circle, and the equation is I du dt, so u is a function of x and t, equals pi applied to this nonlinear term u squared u. And what is pi for a function f expressed in its Fourier series? It is a projection on the positive wave numbers. So it's a non-local operator. It is an integrable, completely integrable system, Hamiltonian. And Patrick Girard and Sandrine Grelier studied this equation in very much details. And in 2017, they showed that the HS norm of this function grow in time. And not only they grow, but there is a relation between the growth of this HS norm with wave turbulence, in the sense that, well, they prove that limit sup as t goes to infinity of u in HS goes to infinity, and limit f is bounded. So somehow, not only that generically the HS norm grow, but there is infinitely many transitions between low and high frequencies. And in the terminology of wave turbulence, it's often called forward and backwards cascades of energy. So that was this very precise result, and was obtained by Girard and Grelier on that cubic Szego equation. Another problem that also received a beautiful advance recently by Girard, Capeller, and Topalov. They studied the Benjamin-Ono equation. So Benjamin-Ono is also an integrable system. It's a one-dimensional, and it's a model that was obtained by Benjamin and Ono in the context of to describe internal waves, long waves in internal waves in a two-layer fluid. And it looks like KdV, except that the third derivative here is replaced by the Hilbert transform applied to the second derivative. So that's a Benjamin-Ono. And they proved global well-posedness for U0 in HS for S larger than -1/2, which is an optimal result, as this S -1/2 is again the threshold for well-posedness. Now, I thought I would show also this result by Koch and Tataru that concern the two equations. On one hand, 1D NLS focusing and KdV. And So as we know, the inverse scattering, these two models are integrable by inverse scattering. The classical methods of inverse scattering show that these equations have an infinite number of conserved quantity, countable infinite number of conserved quantities. And Koch and Tataru, they extended this countable family of conservation laws to a continuous family. And this continuous, this conserved quantity, they are equivalent to HS solutions with S larger than 1/2 for K for NLS and larger than -1 for KDV. So the last example that I would like to show is a two-dimensional model, the Davis-T-Watson system, that is also a model coming from the water wave in the three-dimensional water wave in the presence of surface tension in a shallow water regime. So it has a form of a Schrödinger equation with an additional term here that is non-local. Phi x is come from, sometimes it's called the mean field. It satisfies Laplace equation. So theoretically, one can solve the phi in terms of u and put it back in the equation. That gives a Schrödinger equation with a non-local term, two non-linear terms, one local and one non-local. And one observes also that here we don't have really Laplacian, we have hyperbolic operator that makes the analysis very difficult. This is an integrable model. It's very specific. It's because of this, well, for certain parameter, in particular the presence of these two, it is an integrable system. And Peter Perry showed that the problem is globally well posed and he also established the long time behavior for initial condition in H11. That means that the solution, the function u0, the initial condition is in H1. So the function and its derivative is in L2. And there is also the second one refers to the decay. And it was recently extended to initial conditions that are only L2. And again, this is optimal. So although it really does not relate immediately to DNLS, I thought it would be interesting to share some recent progress in this integrable equations. Okay, so now I'll go back a little bit in time, and I would like to give a little bit of historic context about completely integrable systems and see how the progress have been accomplished. So there is a very nice review article of Percy Dived that is called "What is an Integrable System?" It is published in the Proceedings of the Fields Institute in 2019 that followed a summer program, 1 month program on nonlinear dispersive problem and inverse scattering. And so that's a very interesting and broad article. Now, the notion of integrable systems originates from in the 17th and 18th century, with the goal of integrating in an explicit form some dynamical systems. Now, the modern theory of integrable systems is attached to the discovery in the 60s of a method to solve Korteweg-de Vries equation in terms of spectral and scattering theory of the Schrödinger operator. minus the xx plus u, where u is a solution of Korteweg de Vries. And that was the beginning of the inverse scattering and the seminal paper by Gardner Green, Krushkal and Mira. This method of solving KDV was very shortly followed by the discovery of what we call lax pairs by Lax, which says that if you solve the Korteweg de Vries equation, then there is these two operators, and that's the pair L and B, such that U being a solution of this KDV, then there is a relation between L and B in this form. A consequence of this lax pair is also that the spectrum of this operator L does not change in time. People call that, we say that it is an isospectral deformation of for the operator L. And the consequence is the existence of an infinite number of conserved quantity. Now, these discoveries were followed by, in the 70s, by the observation that these lax pairs exist also for other equations, nonlinear Schrödinger equation in 1D, Sine-Gordon, also the Toda lattice, which is a discrete model in for solids, for crystals. And there is this picture that is very common to draw to illustrate what does inverse scattering mean, and what does this picture say? It says that if one starts with an initial condition U0, the question is to find a scattering map, a map that I called R here, that associates to the initial condition a set of scattering data associated to a linear operator L, this linear operator that I mentioned earlier. This set of scattering data may be more or less complicated depending on the situation. What is very special about this data is that their evolution in time is simple, it's linear. And the next step, which is usually very difficult, is to understand this map R and its inverse sufficiently well so that one can go back and find and reconstruct the solution U as a function of T. Sometimes it's called the reconstruction of the potential for all time. And at the same time, one would like to understand even better its behavior as T goes to infinity. So that's the general picture. And I would like to illustrate this model on the defocusing NLS equation, which is written here. As you see, there's a minus sign here, which is, so it's the usual NLS equation with defocusing in one dimension, for which Zakharov-Shabat in 72 and followed by Ablowitz-Karp, Newell-Seeger developed inverse scattering. And in this presentation, I will also discuss the work of Daift and Zhu in 2003 that provide a very precise behavior as T goes to infinity, and also provide the tools, new tools compared to the older work. Okay, so this is our initial equation. And again, the first step is to find lax pairs. And the nonlinear Schrödinger equation is the consistency condition for this system that is written below here, that is overdetermined. So psi-x, deep psi dx equals L psi and deep psi dt equals B psi. These two operators L and B were discovered in, I think, for the first time in Zakharov-Shabbat, 771. And they satisfy the lax pair. In this book that I mentioned earlier, there is also a review article of Peter Perry that explains the different steps in this problem. So in this system, psi is an unknown 2x2 matrix. There are several notations. Lambda will play the role of a spectral parameter. Sigma 3 is a third Pauli matrix, 1, 0, 0, minus 1. The capital Q and capital Q tilde are related to the solution of the NLS through this matrix, are constructed in this way. And so these are the two equations, one deep psi dx, deep psi dt. So the first important observation is that the first important element is to study this problem, the first equation. It is an eigenvalue problem that can be written L psi equals lambda psi. Well, L is this operator. And the first, in following the diagram, the first step is to find the scattering transform. So if Q equals 0, so if there is no potential here, well, the solution is of this eigenvalue problem is that the operator has a continuous spectrum R, bounded solution, and bounding solution in this form. Now, if Q is in L1 and the lambda is in a continuous spectrum, there exists solution that we call L plus and minus that to this eigenvalue problem that behaves in this way, and these two solutions are called as, oops, I should have said as x goes to plus and minus infinity, something is missing, and they are called the Yost solutions. So it's possible to show that these two solutions that behaves in this way as x goes to plus or minus infinity are related by a transition matrix that has a determinant equal 1. And in this case, this is a kind of a simple case where the direct transform, scattering transform, associates to Q, the potential, the solution of NLS, this function R, which is called the reflection coefficient, which is the ratio of P over A. And it's important to see here that this relation shows that A cannot vanish, never vanishes. The next step, so that's the direct transform. The next step is the time evolution. It evolves very simply, like very linearly. And the third step is the inverse map, which how to recover if one knows this, if one knows the reflection coefficient, how can we construct back the potential? So in the original papers, it was done through the Gelfand Levitan-Marchenko formula. And Abrowitz-Segur, Zakharov-Manakov, they analyzed, they gave very precise formula on the large time behavior depending on these initial conditions. Now, in the 80s, it's proposed a new method to recover the potential through a Riemann-Hilbert problem. And there was many advantages to this formulation, in particular, a more systematic that allow the more systematic mathematical analysis of these maps. And it was the work of Bill Kaufman, Bill Dive-Tomei, Zhu, Dive-Zhu, and many others. There is a very nice paper, review paper again by Dive-Zhu that presents these ideas. So what is the Riemann-Hilbert problem in this context? Well, assume that R0 is given, that's a reflection coefficient at time t equals 0, fixed x, fixed t. The question is to find a matrix that depends on x and t that are fixed and the spectral parameter z, so that M is analytic on the both sides of the real axis, on the upper and the lower plane. It has continuous values as the parameter z approaches the real line. It behaves like infinity for large z, and the jump matrix is given in terms, and the jump is given in terms of the reflection coefficient in this form, where theta is called the phase function is written in, is given by this formula. It depends on xt, they are fixed, and the parameter lambda. And from this solution M, the potential, the solution, from this solution to the Riemann-Hilbert problem, Q, the solution of NLS, is given by this limit as z goes to infinity. M12 is the entry, the M was a matrix, so it's a matrix, the entry 1, 2 of this matrix. So it's a very beautiful formula, and the large time behavior is obtained by many reduction of this Riemann-Hilbert problem. In particular, for large T, this Riemann-Hilbert problem reduces to one that has non-trivial jumps only in the small neighborhood of the stationary phase point. And more beautifully is that after a number of reduction, this Riemann-Hilbert problem becomes a universal one, solvable in terms of special functions that are particular solutions of that are the solution of particular ODEs, the parabolic cylinder equation. So it's a very beautiful derivation leading to a very universal Riemann-Hilbert problem. And the methods that are now well understood are called the method of nonlinear steepest descent due to Dive-Zhu. And there are some variants of this method allowing some non-analyticity in the Riemann-Hilbert reduction involving debug problem. So I will finish this section by not commenting too much because I need to go to the derivative NLS. But this is the theorem of Dive-Zhu that says that as t goes to infinity, it provides a very explicit formula for the long time behavior, and the various coefficients that appear in this formula are all related, only related to the reflection coefficient associated to the initial condition. Finally, I would say also that there is a Plancherel identity, a little bit like in Fourier transform, that the L2 norm of Q is equal to the L2 norm, to this integral of this quantity constructed from the reflection coefficient. Okay, so now I think in the time that remains, I will like to discuss what happens for the derivative NLS and some difficulties that come up that we have not seen in defocusing NLS. So first of all, the Lax pair the lax pair and the question, what is the scattering data? How can we construct the scattering data given the initial the function, the initial condition, Q0? Well, the goal is to choose the scattering data so that the inverse scattering problem will allow the reconstruction formula. And so the first step is the study of the spectral problem. The spectral problem here is a little bit more complicated than that of NLS. In particular, it involves the scattering parameter with a square. It's sometimes called the pencil operator pencil. And the solution, the Yost solutions are constructed as before, but the continuous spectrum is composed of these two lines, R and IR. Again, there is a transition matrix. Maybe I will not go too much in the details, but it's an important observation that there is a change of variable that is called, that here lambda is zeta square, that exploit the many symmetries that happened in this transition matrix that permit to write a new spectral problem for this variable that in particular transform this contour, to the straight line, to the map, to the real line. And maybe I will not go too much into details, but there is a reflection coefficient that is constructed again from this transition matrix, and there will be different scenarios. The role, first of all, this A alpha may have zeros. It may have zeros, we see it from here, it's not forbidden. It may have zero on the real line, it may have zeros on the, it has an analytic extension on the lower half plane, so it may have zeros on the lower half plane, and there will be different scenarios. So here, the first scenario, so there are two functions, alpha and brev, alpha brev, they are related by some symmetries. So the first scenario is that this alpha brev has no zeros, and then the direct map is simply to Q associate the reflection coefficient. For example, this happens when Q is small in some norms. The second scenario happens when alpha brev has a finite number of zeros in C+, but no zero is in R. This is called the generic potential. And these zeros in C+ signal the presence of bright soliton in the large term asymptotics. Then the direct map becomes Q gives the rho, the reflection coefficient, and this constant, lambda n, the zeros of alpha, and some additional constant that come up in the picture. So for example, if Q is the bright soliton that I presented earlier, its scattering data are rho equals 0, it's called reflectionless, and it has only one zero, lambda 1, and one constant C1. And this, so that makes 4 parameters because lambda 1 is complex, C1 is complex. These 4 parameters are related to the 4 parameters of the bright soliton that I showed earlier. In particular, the real part of the lambda 1 is related to the velocity. So the real part, the velocity is minus 4 times the real part. And all the other coefficients appear here. This soliton is exactly the same soliton as I showed before. You see here. And then well, there is also the notion of n-soliton. So n-soliton is not so easy to write in physical variables, but in terms of scattering data, it's again reflectionless and a finite number of scattering coefficients here. Now, there is another case, which is a difficult case, is when this alpha brev has zeros on R. That makes the situation very difficult because that makes a singularity for the reflection coefficient. And in this case, that these zeros are called spectral singularities. So here we used an idea of Xin Zhu that he developed in these papers. He developed new tools to construct these direct and inverse scattering maps that are somehow insensitive to singularities of the spectral data. So he proposed that one define the scattering data in the following way: to Q, to the initial condition or the function, one associates on one hand the reflection coefficient, and then jumps around associated to a Riemann-Hilbert problem along an augmented contour. So this contour contains all the zeros that are on the complex plane, and are also the zeros on the real axis. And it's large enough to contain everyone. And this will be the contour in the Riemann-Hilbert problem, which is more complicated because it's self-intersect. So it contains the real axis, the half circles, and the inside also here. Okay, so I will maybe pass this a little faster. Well, the time evolution of the spectral data, just in the case of forgetting the spectral singularity for the moment, evolve like before, with very simple time evolution. And the inverse map is again defined by a Riemann-Hilbert problem. And this Riemann-Hilbert problem, I will not go into the details here. The formula is similar to the one I presented for defocusing NLS. What is really more difficult here is what is the contour and what is the contour where the jumps happen. And it will be a different setting again, either the real line when alpha has no zeros, no spectral singularities, or a real line augmented by small circles around the finitely many zeros, lambda k, or in the presence of zeros and spectral singularity, the contour that I showed a little bit before. So this involves a little bit more technicality, but this is the fact that we were able to deal with the spectral singularities allowed us to have no assumption on the initial condition to prove the global well-posedness. So that was the effort. And so finally, I will, this more or less repeats the long-time asymptotic and soliton resolution for the DNLS equation that I presented earlier. Maybe I will not go too much in these details. A consequence is the asymptotic stability of one soliton solution and n soliton solution that claims that if one starts with initial condition close to n soliton, then assuming that the scattering data are close to the one of the soliton 2, as t goes to infinity, the solution of the DNLS equation separate in a sum of n one solitons that move with different velocities and separate. And I will conclude maybe the talk by discussing some questions that are under investigation that for now has no progress, but one is that the long time behavior and the separation in different separated solitons is obtained in the absence of spectral singularities. So the question is, what happens when spectral singularities are present, and what are the effects? So we know the solution exists for all time, but what are their effects on long time behavior of solutions? Is it possible to reduce the regularity assumption on initial condition? We had solutions in H22, so we assume quite smoothness and decay. And finally, something that we're not yet able to address is what can we say about the algebraic soliton? Are they asymptotically stable? And at this, from here, I will just thank you very much for your attention. Thank you.
Well, thank you, Katrine. There were some comments in the chat. Maybe would people like to ask some questions?
Can I see the chat? Or
I think if you are not doing full screen, then you'd be able to see the chat.
Oh, okay. Let's see if I can see the chat.
If you mouse to the bottom of the screen, you should see the chat as an option.
Oh, it doesn't appear, but maybe we are
there. Well.
Yeah. No, I don't see the chat. Oh, maybe more.
It'll be in the Zoom window.
Yeah. Okay. Oh, see, that's okay. Also, Jim, do you want to read your question?
Sure. So I have two questions, one related to the chat and one that's kind of different. Are there any breather-like solutions or things that aren't necessarily solitons that separate in this equation?
Yes. In fact, in this presentation, I essentially assume that the real part of all this lambda k are different, meaning that the velocity are different, the different velocities. But there are situations where lambda k may have the same real part, which indicates that the soliton move with the same velocity. So then there are some interaction and they produce some kind of breathers. We have not explicitly worked out the details, but we believe that they will give rise to some breathers.
So in some sense, the results that by the way, the results are really awesome. Congrats. But these are characterizations of solutions that you design with the appropriate hypotheses rather than statements about ultimate emergence on arbitrary initial conditions. Is that a fair characterization?
So for the long time, for the global well-posedness, the only assumption is that Q is in this weighted Sobolev spaces. But for the long time behavior, there is this additional assumption of genericity, which refers to the fact that the spectral data of the initial conditions do not have spectral singularities.
Okay. And then I had one other question, which might be more optimistic than I have any right to pose, but I'll ask anyway. So this recent work by Nakman, Rezev, and Tataru improved in Davy-Stewartson the prior work of Peter Perry by taking an H11 assumption for Davy-Stewartson and converted it to L2 by doing some sort of nice harmonic analysis related work. Your result is an H22 setting with a result that might ultimately become phrased in L2. Is there any hope that this Nachman-Regev-Tataru type of approach could release the regularity and weight assumptions and get down to this natural space rather than this weighted space with higher regularity?
So the natural space would be H1/2, like it's like in your work.
I'm sorry, I misspoke.
Would be the best. Now, Nachman, Regev, Tataru, they worked with the inverse scattering method in 2 dimensions, which is very different from the one in 1 dimension. It involved the D-bar problem. For example, the direct and inverse map is the same, but there are other difficulties. So I believe there will be not necessarily their approach, but certainly a lot of harmonic analysis. Yeah, so I don't know, but it would be nice to have H1/2, but we are not there. I mean, at least in this setting of, yeah.
Thank you very much.
Adrian, do you want to ask your question?
Is there any condition on the initial conditions to get purely imaginary eigenvalues? So I think if you work with this variable lambda, which comes after the transformation, that transform the 2 axes to the real line, well, this the spectral singularities will be on the real line, right? But these spectral singularities on the real line, I think they correspond, if you go back to the original spectral variable zeta, I think they correspond to a point on the imaginary part, but I'm not exactly sure. They correspond to one of the axes. I don't remember which one. But yes, in the original variables, these spectral singularities, I think they appear on the real on the imaginary axis. But I would have to check that. I cannot be 100%. I don't know if it is what you were asking. Okay.
Okay, any other questions? Kathleen here. Well, then I think we should thank Kathleen again for both of her very nice talks, and congratulations. And
well, thank you very much. Thank you for your kind words and for listening these 2 talks. Yes, thank you. Thank you to everyone.